Not that you can't, it's that you're not willing to. Okay. So 11.3, surface area of pyramids and cones. Now, we talked prior about relationships between prisms and cylinders, and how a prism evolves into a cylinder. Okay, the more sides that we add to it. Same thing happens with pyramids and cones. So learning stuff about pyramids will help us eventually kind of evolve into learning something about cones. And then collectively, as a group, all four shapes actually have some linkage to one another. Cones and cylinders will have a nice common link. Pyramids and prisms have a nice common link. And we'll talk about those things as we progress through. Eventually getting into volume, maybe late this week and early next week. All right, so just by definition, a pyramid is a polyhedron, or a three-dimensional shape, in which one face, which we're going to call the base, or one surface, can be any polygon that it wants to be. Okay, so the base can be a triangle, can be a square, can be a pentagon, hexagon, octagon, dodecagon, whatever it wants to be. Okay, and it can be regular or irregular. That base does not have to be regular. Okay, it does not have to be equilateral and equiangular. However, those are the ones that we will spend most of our time on, if not all of our time on. Okay, because they set themselves up nicely to be able to be addressed with some nice, convenient formulas. Okay. All the other faces of the pyramid are referred to as lateral faces again, and they meet at a common vertex. And that vertex is referred to as the vertex of the pyramid. And you see in the bottom picture down there, obviously the base is the hexagon. Okay. All the triangles are what we call our lateral faces. And if we look at all those triangles and look at the fact that all meet up there at the top, at that vertex, we call that the vertex of the pyramid. Okay. Now there's a couple other things that are on there. Lateral edge. Okay, that's where two triangles share a side. Okay, so that's a lateral edge. This is a lateral edge, so forth. Obviously, lateral faces are all of the triangles. Any one of the triangles is called a lateral face. Now, the altitude of the pyramid, and we got to have that kind of phrase on there, of the pyramid, because there's all types of shapes there, right? Okay. There could be several different altitudes. We got to make sure we're talking about the right one. Okay. The altitude of the pyramid is that red dot line. I'm going to go to GeoGebra here in a moment to help you see that a little bit better. But that's where we draw in the altitude. That's the easiest place for us to determine the altitude of the pyramid. We won't use that value kind of directly today. The altitude, or h, of the pyramid, we won't use directly for our formulas, but it is important for us to know so we can find some values for our formulas. Base edges are the edges that a lateral face and a base share. Guys, we're seeing these down here. These edges of the hexagon are called base edges for the pyramid. So looking at a three-dimensional kind of rendering of this, so we can kind of mess around with it and rotate it and analyze a little bit better than what that static picture is able to do. We see here that this is a triangular pyramid. Okay, the base, okay, this base down here, I just highlighted, is a triangle, so obviously a triangular pyramid. Now that thing can change, and we can see we have a square pyramid. And those are probably the pyramids that you guys are most familiar with. Those are the pyramids in Egypt, right? There are some pyramids in Rome that are that way. Pyramids in South America that are that way. If you've ever been to, has anybody ever been to Paris, France? Been to Paris, Texas? All right. Do you guys know what the Louvre is? Art museum in Paris. Okay, it's where the Mona Lisa is. Okay, out front, you guys have watched what's the movie? Not Angels and Demons. What's the one before that? Da Vinci Code. You guys seen the Da Vinci Code? Man, you guys are missing some good movies. You guys live in caves, don't you? All right, so the Louvre, let me see here. L-O, L-O. Okay, so this is the Louvre in Paris. That is a square pyramid. Okay. If you guys haven't watched The Da Vinci Code, it's a great movie. Go watch it. All right. So those are the pyramids that we're maybe most comfortable dealing with or experienced in real life. But you can add sides and you can start getting these. What is this starting to look like? Maybe if I bring that down a little bit more. Maybe you used one yesterday morning. Looks like an umbrella, doesn't it? Okay. So your umbrellas are maybe fashioned somehow as a pyramid. Okay. Tops of silos. Okay. You guys know what a silo is? Okay. Like a grain silo or something like that. A lot of the tops of them are pyramids. Anybody know what a gazebo is? All right, so people that have gazebos, a lot of times the roofs of those things are pyramids. Okay. So I'm going to go back to maybe, let's see what the hexagon one. Sabrina, did you have a question? Well, if we can do that in one day, maybe we will.
Well, maybe. At least watch part of it.
All right.
Cool, you can watch the Da Vinci Code.
So that blue segment up there, that blue segment is our altitude of the pyramid. Is that all right? Okay. And it's the altitude of the pyramid because it is perpendicular. It is perpendicular to the base. Okay with everybody? Okay. Yes. Okay, so we could take, and I can't do it here, but I could maybe take this. Maybe I can. Control C. V. Oh, yep. Okay, so that is the same height, okay? But now it's outside, right? So putting it outside the figure or anywhere else in the figure doesn't lead us to maybe some of the geometry that we're going to need. I don't know why I can't move that. But yes, that so you can always cut that out and put it anywhere you want to, but it has to be the same height and still has to be used in the same fashion as that one on the inside. Does that make sense? For the most part, we'll never have to move it. We're just going to stay with that. Okay? Now, here's the thing. There probably, and this especially occurs when we start talking about volume here in a little bit, maybe Friday or Monday, or not Friday, Monday or Tuesday. If I need the altitude for some reason, a lot of times they don't give it to me, and we have to use our kind of preliminary geometry to develop it. Okay? And that preliminary geometry is by doing that. Okay? So I create that red segment, and then I'm also going to create that red segment. Okay? So you see that triangle on the inside there? What kind of triangle would that be? It'd be a right triangle, okay? And it is going to, okay, so that triangle on the inside, let me get rid of this face here just to make it a little bit easier. Okay. All right, so we see that right triangle on the inside. Obviously, the blue distance is the altitude of the pyramid. What is that red distance on the bottom? Good. It's the apothem of the hexagon. We can kind of visualize that and view it that way in a 3D dimensional shape. Okay. So they might provide you with that information And we might, for some reason, you're going to see here in a little bit the reason, we might need that red dotted line. So using the altitude of the pyramid and that apothem will help me with the Pythagorean theorem to find that red dotted line. Is that okay there, everyone? But that's not the only triangle that can show up, or that exists here. Would you agree that that is another right triangle there? Okay. Now if I look at that base, is that the apothem anymore? It's a radius, right? Okay. And now this blue is obviously still the altitude, but now look at this red distance, which is the hypotenuse of that inside triangle. That is the side of one of our isosceles triangles, right? Okay. Something else that I didn't mention, I guess, when we go back to this triangle, if I look at that red line right here, and let me actually make it a different color so I can talk about it easier. If I look at that purple line or pink line, what is that for the isosceles triangle? If let's say the pyramid was all made out of glass, and I was able to take the panes of those individual panes of glass out and lay it on the ground, what would that purple line be for that one triangle? So we kind of see what I'm saying here. If I were to take this triangle out, DCE, lay it in a two-dimensional, or as a two-dimensional shape, that purple segment would be that one there, right? This is an isosceles triangle, isn't it? Okay. Is that going to be perpendicular right there? So this is the altitude, this purple line here, which is, again, the hypotenuse of that triangle on the inside. Okay. But that purple line is the altitude of one of the lateral faces. Okay. It divides that angle up there in half. It cuts this thing down here in half. Okay. It's that common segment that we've been talking about all the time for isosceles triangles. That is the perpendicular bisector of the base. It's the angle bisector of the vertex angle. All that kind of stuff for an isosceles triangle. Does that make sense? Okay. Another triangle that we're used to, or that we're going to get used to and need to use, will be that triangle right there. Okay. Which is a triangle that is part of or half of your lateral face, right? Is that a right triangle as well? Okay, so generally speaking, the reason we're looking at these three different triangles, or we're going to need to analyze these three different triangles, is because this distance right there, that green distance, becomes very important for our formulas. Okay, and we need to come up with that. Okay, or we're going to have to come up with it in several situations. That green distance is called the slant height. Okay, right here in this picture, it's that red line on that yellow surface. Okay, which it's the altitude of that two-dimensional triangle, right? If I take that triangle and lay it in a two-dimensional plane, that L that they're referring to is H for a two-dimensional isosceles triangle. It's the altitude of a two-dimensional isosceles triangle. Okay. Now, we don't call it H of the pyramid because that's already been defined as the altitude, right? So the altitude of the pyramid, or H of the pyramid, is that dotted line on the interior that goes from the vertex perpendicular to the base. Okay. We refer to that L, or that altitude of the two-dimensional isosceles triangle, as the slant height. Okay. And we call it the slant height of the pyramid. Okay. Because if you were, in front of a pyramid like this, and I told you to crawl to the top of it, okay, that would be the shortest distance that you would climb to the top of it. Does that make sense? Okay. And that's going to be a component for some of the formulas that we deal with here in a little bit. And that's just kind of just a rough rendering of the next slide that I was going to show you, but I think it's a little bit better to look this way. What would you call that thing there for your pyramid? That's the net of the pyramid, right? Okay. So it's taking this shape here, okay, and basically unfolding those triangles and laying them flat. And I could then look at this, and if I were to look at that and lay all these triangles flat, and I added up all those triangles, the sum of all those triangles would be the lateral area, wouldn't it? Okay. I want to come up with a formula for the lateral area. If I were to look at just one of these triangles, let's just look at this top triangle. So we're going to look at that yellow one. This distance here, okay? Now, for the pyramid, so for the triangle, you call that h, right? It's the altitude. But for the pyramid, don't we call it L? That's the slant height. Okay? Now, I'm going to call this distance right here S. Okay? And just for the side length of a base. Okay? I want to find out the area of the yellow triangle. And we know that area of a triangle is 1/2 BH, don't we? Okay. What would you say B is for this yellow triangle? That's the S. And what is H? L. Okay. So now we just found the area of that yellow triangle in terms of the components for the pyramid. The slant height of the pyramid and the side length of the pyramid, or the base side length of the pyramid. How many of those triangles do you have? Yeah, so lateral area here would be 6 times the area of the yellow triangle, right? Okay. Now, bear with me here because I'm right now dealing with 6 sides, but if I were to look at 5 sides, now I would have, now everything's messed up, but you can kind of maybe visualize that you would only have 5 triangles, correct? If I had 4 sides, I would only have 4 triangles, okay? So this number on the outside here, this 6 is going to vary from shape to shape, from pyramid to pyramid. Is that okay? So when I ask this question, when I take 6 times 1/2 SL, some people are going to say, well, let's take the 6 times the 1/2. That gives me 3, right? And I have 3 SL as the area for the formula for lateral area, which is great. It is. But then when I go to 8 sides, if I go to an octagonal pyramid, now I have 8 times 1/2, so it becomes 4 SL. Which is a different formula now, right, than 3 SL. And when I go to 7 sides, now it's 7/2 SL, or 3.5 SL. So it's a different formula every time I have a different shape. Does that make sense, everybody? So I'm going to use the commutative property and the associative property in a little bit of a different way here. And I'll move the 6 right next to the S, and I'm going to group those two together, and then multiply by L. Is that still the same thing? Does this product here still say the same thing that one does? Okay. But now look at what 6S Let's look at what 6s would represent. That'd be 1s, right? That'd be 2s, 3s, 4s, 5s. That'd be 6s, wouldn't it? What is 6s for this hexagon? It's the perimeter. So that thing changes to P, and then we have times L. And what's nice about that is because now if it's a pentagon, it's 5s. Well, is 5s the perimeter of the pentagon? If it's a square, it'd be 4s. Is that the perimeter for a square? So regardless now of how many side lengths you have, or how many base edges you have, that is always P. It's always the same formula for an infinite number of shapes now. Does that make sense to everybody? All right. But the development of that formula, if I just say it's 1/2 PL, take my word for it, people are going to be like, well, okay, I can do that, but I don't understand why. Do we understand that we're just summing up 6 triangles here? And this does it a lot quicker, okay? Now, the issue at hand is where does that L come from, okay? And we're going to have to do a little bit of work a lot of times to find that L, okay? And that L is going to, again, be part of that triangle there on the interior, okay? So that's probably 80% of the time that's the triangle that you're going to use to determine L, okay? But you might have to mess around with some other triangles based on what they provide you. Is it okay with everybody? So 1/2 PL is your formula for lateral area, okay? And then if I want to find surface area, well, how many bases do you have? Just one. So surface area for a pyramid is LA plus 1B. And again, B can change, okay? B could be, we talked about regular polygons for the most part, and that's what we will talk about for the most part. But it could be a parallelogram, it could be a rhombus, it could be, a trapezoid, all those things. It doesn't have to be regular. I don't know if I still have it here or not. Let me just zoom out. But we could have well, there you go. So we could have, that's a pyramid still, okay? But it's not a nice pyramid, okay? Because obviously it's slanted, so the word oblique comes to mind, right? Okay. The base is not regular, okay? So the formulas that we are going to use today maybe don't really address the surface area of that pyramid as well as they do if it's a regular pyramid. Does that make sense, everyone? Huh? Not early on. Okay. If I wanted you to find the surface area of this thing, what would be maybe the best approach? Find the 4 individual triangles down together, right? And then maybe try to deal with chunking that shape up and determining its areas, and then add all that stuff together. Does that make sense? Because it is irregular, so you're going to have to do that chunking process to find total area, surface area. We're going to focus, like I said, a lot on just these types here. Okay. As we read this, says this example gives a lot of the information that you need to simply just pull it out of the picture, plug it into the formula. Okay. As the problems get more and more difficult, those values that we're just pulling out here become kind of implied values, and you got to do maybe 1 or 2 or 3 kind of sub problems to generate them. Okay, so make sure that we're paying attention to that process. If we want to find the lateral area here and then the surface area, it's probably a good idea to write your formulas down. So I'm going to say surface area is LA plus 1B. Okay, LA in this case, because it's a pyramid, it's going to be 1/2 PL. And now B, capital B, what is the shape of the base here? Hexagon. What is the formula for a hexagon's area? 1/2 AP. Okay. So when I look at this, okay, 1/2 P, what is the perimeter of your base? Yeah, it'd be 36. It'd be that distance there 6 times, right? So 36. And now L, what is L? What is the slant height of your pyramid? It's this 9 over here. Okay, that's your slant height. So you see how that was kind of easy, right? Because everything was already provided for us. So that's 18, 18 to 7, 162. The lateral area is the sum of these 6 triangles. That work right there is finding the lateral area. Now I want to find the base. Okay, so 1/2. What's your apothem here? 3 radical 3. Again, probably if I'm asking to find the surface area, they're probably going to hide the apothem to me. They're going to make me work for that a little bit. What is the perimeter? 36, right? Once you found the perimeter over here for lateral area, it's the same base over here, right? So 1/2 of 36 is 18. 18 times 3 is 54, right? What do I do with those 2 numbers to find my surface area? Add them together. So I can't physically combine them, right? I can't rewrite it as a new expression. But I can just smack a plus sign between them and say 162 plus 54 after 3. And that'd be my exact area for that pyramid. Is that right? Okay. So let's do one that's maybe a little bit more difficult. All right. This is a pyramid in Rome. Pyramid of Cestius. And they just want the lateral area here. Okay. And you see that they don't provide you everything directly. Okay. Hopefully we can find the perimeter pretty easily. What's the perimeter going to be here? 120. Okay. It's a square pyramid. If they don't say that it's regular, make that assumption. Okay. So this is a square pyramid. What is the process for finding L? L is that distance there, right? Would you guys agree if I took that yellow triangle out, L is what we're looking for? Good. Okay. So this distance here from C to A, that's your apothem of your square. Okay. Which we don't deal with a whole lot, but your apothem of your square is always half the side length. Okay. So side length is 30, so the apothem is 15. So now, that is a right triangle in there, correct? I should be able to take 36.4 squared plus 15 squared. That's going to equal L squared, right? So what would I do with this sum here to find L? Okay, add them and then what? Yep, take square root. Okay, so if I take square root of that stuff, 3 36.4 squared plus 15 squared. That gives me L to be 39.37. And I can multiply that out then and get my lateral area. Okay, now that's a question where because the 36.4 was a decimal and I swear that it's kind of an ugly decimal, so we're not going to write that as an exact answer. We're going to leave it as whatever that target 1/2, 120, 39.37. It's okay. That's just lateral area. What would I have to add to that to get surface area? The base, which is going to be how big? The area of the base is 900. Okay. So surface area would equal that number, plus 900. Okay. Is that all right? So let's get to one where it's a little less informative. No. Come up. Do this one. It says, what's the lateral area? And then eventually we want the surface area. And we're going to leave things as exact values. Okay. So your surface area, again, is LA plus B. We know LA should be 1/2 PL. So we'll figure out what that is. And then B, again, 1/2 AP. So let's go through and find our lateral area. Okay, so 1/2. What's the perimeter? So we have that times 6. We should be 216. Now my slant height. Do I have my slant height in the picture? No, it's that distance right there, isn't it? Okay. Is that part of the triangle where that distance is 42, that distance is 18 radical 3, and that distance is L? Can I use Pythagorean theorem here? Okay. So I'm going to say L squared is equal to 42 squared. 42 squared is 1764. Okay. Plus now I'm going to square this number. Okay. So again, I'm squaring both these. 18 squared is 324. What is radical 3 squared? 3. So when I take 1764 and add to it 324 times 3, it gives me 2736. That's L squared. So L is going to be the square root of that, right? Okay, 2736. So I look at that number and I look at the problem. It says leave the answer as an exact value. That number probably needs to be reduced, right? We need to start seeing if there's any perfect squares inside that large number, 2736. When I told this for the last class, when I look at that, and I don't know if this is always going to work, okay? If I see 27, I see 36 in that number, and both those are divisible by what number? 9. So 9 is maybe a number I want to check. Maybe I see this 36 here, and I want to check 36. So I'm going to take 2736, I'm going to divide it by 36, and just see what happens. It gives me 36 times 76. Does that make sense? Okay, and that should still all be underneath the square root. But now, would you like to deal with the square root of 36? Is that pretty easy? Okay. And now if I want to simplify 76, because there might be still a perfect square inside 76. The only numbers I have to check are the perfect squares that are less than 36 now. Or sorry, less than 38. So I take half of 76. Remember doing that process? Okay. So I look at half of 76, that's 38. And now I got to check the numbers that are less than 38. That would divide 76. So one perfect square less than 38 is 36. Will 36 divide that 76 evenly? Nope. The next one's 25. 76 does not end in a 5 or a 0, so 25 is not going to work, right? The next one is 16. Okay? Well, 16 times 4, or 16 times 5 is 80. Okay? So that's not going to work. It's not going to divide evenly. So then I try 9. Well, we've already taken a 9 out with that 36. That's probably not going to work. Okay? We get to 4, right? 4 does work. How many times does 4 go into 76? 19 times. Okay? So I get 36 times radical 4 times radical 19. That's how this number right here breaks down. What's the square root of 36? 6. What's the square root of 4? 2. What am I going to do with that 6 and that 2? Multiply them together. And then 19 is a prime number, right? So there's my slant height, fully simplified. And what that tells me, guys, is that if I look at 12, 144 is actually the biggest perfect square that will divide 27 and 36 evenly. Okay? Probably, I'm assuming that many of us didn't recognize that. Okay? That 144 was in there. I didn't recognize it. Not saying that I'm smarter than you or not, but I do deal with them a little bit more than you do. So now I'm going to multiply that stuff together. So that's going to give me 108 there, right? And when I multiply 108 by 12, I should get 1296. Radical 19. That's my lateral area. If I want to find my base, what's your apothegm? 18 radical 3. What's your perimeter? 216. You see how once you do the work to find maybe lateral area, finding the base, a lot of those values have already been found for you, right? Or you've already done the work to find them. So it's going to give me 9 there. 9 times 216 turns into 1944. And then radical 3. So what would I do with those two numbers then to find surface area? Add them together. Can I combine them? Nope. I'm just going to have to write it as 1944 radical 3 plus 1296 radical 19. That would be my exact surface area. Is there something we can do? Hopefully you recognize that procedural-wise, we're not doing a whole lot of new stuff here. Okay? Surface area formula changes simply by, instead of LA plus 2B like it was with prisms, it's now just LA plus 1B. Instead of LA being P times H like it was for prisms, it's now just 1/2 PL. Okay? But procedural wise, you approach it in the same way. Still, we're using a lot of stuff that we've used from hexagons and octagons and those regular polygons to find those areas. Hopefully you realize why, I don't know, 5-6 weeks ago I told when we first introduced regular polygons and finding their areas, 1/2 AP, I told you that was going to be a very important process because of how many questions beyond that use that idea, okay? And that's going to keep on showing up through this week and next week. Tomorrow we'll start class with a couple more examples of this. Maybe show you maybe one of the harder ones where you've got to use a combination of several right triangles to get your slant height. But then we're going to start talking about cones because there's an evolution of pyramids that start making each one of those triangles a little bit more and more narrow. The more triangles you fit in, eventually it starts to turn into a smooth curve, and you start to get your cone. Okay. We'll talk about the net of a cone tomorrow, what that looks like, and then do some examples with that. Okay. Tonight's homework has cones in it. Okay. So whenever you come across a question that has a cone in it, don't do it. Okay.
Don't do it.
Meaning the assignment's not going to be due tomorrow; it's going to be due the next day.
But don't do
Okay.
it.
Do not do the cone ones. I'm not saying don't do the pyramid ones. Do those so that you have questions that you can ask tomorrow before it's too late on Friday when the assignment's due. Can you do the cone one? If you know the formulas.